The first two types of particle motion are going to be the types of movement associated with temperature. Temperature is the motion of particles. The higher the temperature, the faster the particles are moving. The thermometer is like a speedometer. It is telling you how fast the particles are moving. It's not telling you exactly, like it's not telling you 500 meters per second, like I told you the answer earlier. To the average speed of gas particles at room temperature is 500 meters per second. Your thermometer doesn't tell you that, but it's correlated to that. There's a couple other variables in the equation depending on the mass of the particles, etc. But temperature is essentially the speed of the particles. So the first two types of movement are the types of movement associated with temperature. The first one's called translational energy. And if you took algebra and you paid attention and you knew what you were doing, at some point in algebra when you were learning to graph, they taught you to translate points. You would translate points. You would move something from one coordinate to another coordinate. And that's exactly what translational energy means in chemistry. It's moving from point A to point B. So when a particle has translational energy, it's moving from point A to point B. When you drive to school, you're exhibiting, or when you walk to school, you're exhibiting translational motion. You're translating from home to school. And then later, you'll translate from school to the store or to Menchie's. You know you can't translate to Old World Pizza anymore. They closed. Big news of the month, I guess. But anyways, translational movement or energy is moving from point A to point B. That is the primary type of movement associated with temperature. I'm talking to my camera. Okay, I'm standing in the middle of my class just talking, and one of the other teachers walked by and thought I was weird. I am weird, but not because of that. Anyway, so this is the primary type of movement associated with temperature. When you stick a thermometer in the water bath that you had the other day of melting ice, the particles of water were translating, they were zipping around in the beaker, energized on the bottom of the beaker from the hot plate, and banging into that thermometer and transferring energy to that thermometer primarily through translation. But there's another form that is also associated with temperature. Vibrational energy. Vibrational energy is the other form of energy that's most commonly associated with temperature. In other words, when you stick a thermometer in something and it has a temperature greater than absolute zero, we'll talk about that in a moment, then it's exhibiting one of two types of energy usually, or movement. That's either translational in the case of gases and liquids, or vibrational, which is a primary form of movement within solids. Vibrational energy is when a particle is moving backwards and forwards. It's bumping back and forward. If you've ever done those little things where you clack the ball and it goes clack, 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 that's kind of like vibrational energy. The balls aren't moving anywhere. They're just bumping into each other back and forth. Another type of vibrational energy is if you have a molecule, a particle that's elongated. For example, water, with those Mickey Mouse ears, those ears can wiggle. Water can wiggle its ears. So you might see water go through this vibrational thing where the ears are going up and down. Let me get rid of this arrow because that's confusing. So the ears can go up and down. That's called vibrational energy. Okay? Typically, in the ice that you were melting, because the temperature of ice is 0 Celsius, it's not negative 273 Celsius. Because ice is composed of water particles in the solid phase, which I haven't talked about yet, the solid phase, we're getting there. The water particles are not sliding around, they're not translating, they're only vibrating, pretty much only vibrating. And by heating it up, you're increasing the vibrational energy. When you warmed up the ice, you were increasing the vibrational energy. And it increases to the point, it begins vibrating so violently that it begins to tear apart the ice crystal, which we call that melting. So vibration could be back and forth. It could be of a single particle locked into a crystal structure. Vibrational could be a gas particle with its little ears vibrating up and down like that. Carbon dioxide in the atmosphere. Carbon dioxide in the atmosphere does that. It absorbs infrared light beyond red light. And the infrared light causes carbon dioxide's ears to wiggle. Now, carbon dioxide is carbon with 2 oxygens. So carbon's ears are the 2 oxygens. And they'll wiggle up and down. And that's why carbon dioxide is associated with the increased temperature of the atmosphere. As we progress along in our industrial revolution, well, we're well after the industrial revolution, but as we continue to burn organic material and release carbon dioxide as a waste product into the atmosphere, we're increasing the recent concentration of carbon dioxide in the atmosphere. And that carbon dioxide does indeed absorb infrared light, which causes its ears to wiggle. And when along comes a nitrogen or oxygen molecule and it runs into vibrating ears of carbon dioxide, it's like a baseball bat hitting a ball. The oxygen and the nitrogen can go zipping off like home run hits. Now they have translational energy. They have increased translational energy. So we begin to observe, as we increase the carbon dioxide content of the atmosphere, we begin to observe an increase in the average speed of all the other particles. Anyway, vibrational, rotational. Now this is the one I started to write. Rotational energy. Notice if a particle is zipping from A to B, it can collide with another particle and it can pass energy to the other particle. That's why translational energy is primarily associated with temperature, because temperature is the increase, or temperature is the speed of the particles. And if you put something in contact with particles that are moving faster, the faster moving particles are going to collide and transfer their energy to the slower moving particles, and they're going to cause the slower moving particles to speed up or heat up. So it's obvious to see why translational energy can do that. It's like a bullet running into something. It's going to pass energy to whatever it collides with. Vibrational, you can also see why vibrational energy might be associated with temperature. If a particle's vibrating backwards and forwards, it can knock into something and pass its energy onto that thing. Same thing with the ears going up and down, up and down. They can collide with something as they go up and pass energy to that. Again, vibrational, associated with temperature. Even if translational or vibrational energy is possessed by a perfect spherical particle like a helium atom. A helium atom is like perfectly spherical. It can still pass that energy on through collision. But what about rotational energy? Rotational energy is when a particle spins around an axis. Now, imagine if you're sitting in my class and you're on the baseball team and you take your bat out and you start swinging it around your seat. Well, that's not rotational energy. That's vibrational energy in a sense, because you're swinging something back and forth. You're swinging it back and forth. That's vibrational. Anybody sitting around you is going to move out of the way because they don't want you to transfer energy from that vibrating baseball bat to their head or to their stomach. They're going to move out of the way. On the other hand, if you're on the basketball team and you're sitting in your chair and you whip out your basketball and you say, hey, baseball, watch this, and you spin your basketball, nobody's going to be afraid of that. Because even though it might possess the same amount of energy as the vibrating baseball bat being swung back and forth, it doesn't appear that there's any danger of that perfectly symmetrical ball spinning in a symmetrical manner. It doesn't appear that there's any danger of that transferring energy to the person sitting next to you. Even if you say, look, I'm holding that ball on my finger, and you bring it close to somebody, they might kind of go, yeah, that's annoying, get it away, but they're not going to be afraid that it's going to hurt them. It could have the same amount of energy, but because it's symmetrical and spherical and spinning, it's not really going to transfer the energy collisionally. And that's why typically rotational energy is not associated with temperature. It can be if the thing rotating is asymmetrical. If it's asymmetrical and it's rotating, then yeah, it has little bumps sticking out of it that can hit and hurt. If you're spinning around in a circle with your arms extended, yeah, you're rotating and somebody could walk into one of your fists and that could hurt them. It would transfer energy to them. That's different from spinning a basketball that's perfectly symmetrical, because spinning around with your arms extended is not symmetrical in every direction, and it has the potential, the capability of transferring energy by collision. Okay, so in those kind of rotational modes where you have asymmetry, you can actually be associated with temperature. And that brought up what I was saying about the microwave oven. Water is not symmetrical, and if you remember, I said the ears are positive and the face of water is -2. Well, what's a microwave? A microwave is a wave of positive and negative energy. All light is positive and negative energy. It's plus and minus ripples in the electromagnetic field. But it just happens that a microwave's wavelength is proportional to the size of a water molecule, so that as the positive wave of the electromagnetic field, as it approaches the water molecule, the positive of the wave of the microwave will push the positive irs of the water molecule away. In other words, the water rotates. And then along comes the negative trough of the microwave, and it's now facing the negative face of Mickey Mouse, so it then attracts the ears. And we're actually, by microwaving things, we're actually causing water molecules to rotate. But water molecules are not symmetrical. They have these ears sticking out, and those ears begin to bump into other particles that make up our food or our drink, and it then increases the kinetic energy on hold of that substance, which we interpret as temperature. The temperature of the food item or the drink item goes up because we're rotating water molecules with microwaves. The rotating water molecules pass that kinetic energy onto the other particles that are in that food or drink substance, and the temperature goes up. So there's a theory that describes the universe called the kinetic theory of matter, and it describes the universe as just particles, which you and I know as the name atom. So the universe is made up of atoms. These atoms are generally considered to be grouped into one of 4 different arrangements. So I'm going to draw on the screen the 4 different arrangements of particles that you can have. Now, be aware, if you read my notes earlier in October, late October, early November, there's videos, YouTube videos that describe, as well as some paragraphs that describe that there are other kinds of arrangements of particles, other states of matter. But we're going to focus on the 4 most common. We'll start with the solid state. A state of matter, one more time, this is a vocabulary concept. A state of matter is the manner in which particles are arranged and how they behave. So if you have particles that are organized and very close together without moving past each other, if they're locked into position, particles, there's what? 9 particles there. Those particles are very close together. They're so close and they're moving with almost no perceptible motion. We would call that a solid phase. This would be a solid. So in a solid, the particles are closely packed. And we would say that in a solid, the particles have a fixed shape. They're not going to change shape. And a fixed volume. So what does that mean, fixed? Doesn't mean that it was broken and now it's not. It means it doesn't change. So you could say unchanging shape and volume. So in a solid, particles are closely packed. Now there's something else very important that I'm leaving out about solids, and it's the way the particles are moving. And I'm going to tell you this, all particles in the universe are essentially moving. Now, there are rare occasions, but even in solids, the particles are moving. But there are 3 kinds of movement that you need to be aware of before you can understand how the particles in a solid could still be moving. And if you remember back the other day, I told you that temperature is essentially a speedometer of the particles. Temperature is essentially a speedometer for particles. If something has a temperature, then it means the particles are moving. And yet, if you look at a solid, you might ask yourself, well, how are those particles moving and it's still a solid? Well, that's because there are 3 different kinds of movement, and only one of those types of movements produces a fluid-like appearance. I want to tell you which types of movement the atoms possess, or the particles possess in a solid. The types of motion that solid particles possess: vibrational and rotational sometimes. The types of movement that the particles in solids possess are vibrational and sometimes rotational. And this is why a solid like ice, or like the tabletop, like the floor I'm standing on, these are all solids. Steel, aluminum, the things that we hold in our hands, tennis rackets, baseball bats, These are frozen forms of liquids. But just because they're frozen does not mean the particles are not moving. They are moving. If they weren't moving, if the particles weren't moving, they would be extremely cold. There is a temperature, -273, known as absolute zero. -273 Celsius is known as absolute zero. That's the temperature at which it is believed that even in solids, the particles, in all phases of matter, the particles would no longer be moving. Actually, that's kind of, I said that wrong. Because if you've got matter where there's no movement, you no longer have a gas, you no longer have a liquid, you definitely have a solid. The particles are not even vibrating at absolute zero. At -273, it's believed that the particles are not even vibrating at that point. But anything above -273 Celsius, absolute zero, anything above that temperature, the particles are moving. They're vibrating if it's a solid, maybe rotating depending on the particle shape, but definitely vibrating. The particles in a crystal are not going anywhere, but they're vibrating into place. It's like a classroom full of students, all in nice organized rows. It's like a solid, but the students are not perfectly still. Their pencils moving, their arms moving, their heads moving, their knees moving. They're moving in place. They're not translating anywhere, not till the bell rings. Okay, so solids have an unchanging shape and volume. The particles are closely packed, and the movement or motion that the particles have are primarily going to be vibrational, maybe rotational, no translational. If you add energy to a solid, that energy initially goes into the vibrations. As you add energy to the particles of a solid, they vibrate more and more violently. They begin to vibrate so violently that they can no longer stay in position, and they end up ripping out of position. We call that melting. When you add enough energy to particles so that they vibrate enough to rip out of position, they are melting. As they increase in energy, their energy begins to go from vibrational to translational. And then you end up with particles that are farther apart. They're not organized, and they're zipping around in different directions. So there's my liquid, but that's not enough. So in a liquid, here's solid over here. In a liquid, you've given enough energy to the particles in the solid so that they vibrate loose. They begin to move. They're moving translationally. That means they're going from point A to point B. But they're moving slow enough. They're moving slow enough that attractive forces, I'm going to say that their attractive forces hold them close together. Listen carefully. The attractive forces that in a liquid, the particles are moving translationally. They may also be rotating. Depending on their shape, they may be vibrating, but they're definitely translating in a liquid. They have broken free from being stuck in position because they vibrated enough that they broke free. Now they're translating, but they're moving slow enough, or because there's additional pressure from the atmosphere, perhaps on Earth, that forces the particles close enough to feel each other's attractions. Particles like this, whether they're like water, where they have one side positive, the other side negative, or whether they're like, say, helium, excuse me, or something like that, where it's not really sticky. If you push them close together with atmospheric pressure or with some kind of compression, a cylinder, a piston, you force these particles close together. These particles, as we will learn, are not pool balls. They're not baseballs. They're actually, as Rutherford, Thomson, Schrodinger taught us, and some of you are learning about, they're made up of two different parts at least. They have a positive core, and they have a cloud of negative electrons around them. And if you push them close enough together, what happens is the electrons get pushed over to one side. So you have a positive core side and a negative electron side, which makes it kind of like a temporary bar magnet. If you force them together, you push them together with enough pressure, you can cause them to distort and become like bar magnets. So when you have a liquid, it's because the particles are close enough together. Listen carefully, I'm saying this right now, the right definition. A liquid is when the particles are forced close enough together, pressurized close enough together, or slow enough. I said or slow enough, or a combination. They're pressed together or slow enough so that they feel each other's attractions. And those attractions are going to affect their behavior. It's going to affect their flight as they fly through space. They're not going to fly just straight. They're going to, even if they don't collide, if they fly near another particle, it's going to attract them and bend them. So a liquid is a state of matter or a particular organization of particles where they're close enough together and slow enough moving that they can feel each other's attractive forces. Do you need me to repeat that? So liquids have translational. Solids do not. What else do we need to say? Liquids. Let me erase a couple of these liquid particles so I can write here. I'm going to write here. Notice I said here, there's an arrow going from solid to liquid. I said plus energy. It's kind of like solid plus energy will turn it to a liquid. What else do I need to say? The movement is mostly translational, could be rotational, could be vibrational, maybe, depending on the shape of the particle. So I'm going to add rotate. Let me add rotational up here. And maybe vibrational. Remember, for vibrational, you either have to be fixed in position, which is called a solid, and bouncing back and forth, or you have to have 3 or more particles stuck together. They call that a molecule. When you have more than one particle, which we know as an atom, when we have more than one particle stuck together, if it's just 2, it's called diatomic, and it cannot vibrate. If you've got 3 particles stuck together, then it can flex and vibrate up and down like that. So in order for a liquid to vibrate, it's got to be 3 particles or more. Water is like that. Water can vibrate. Liquid oxygen cannot. Gaseous oxygen cannot vibrate because it's only 2, O2. It can rotate, but it can't vibrate. So liquids, the particles are translating primarily. They can rotate. Depending on their structure, they may vibrate, but probably not. What else? In liquids, they can change their shape, but not volume. See, in a solid, you can't change the shape or the volume. In a liquid, you can change the shape, but not the volume. And thank goodness for that. If you drive and you step on the brakes, you're taking advantage of a characteristic of liquids, that they don't change volumes in order to stop. You push down on that brake pedal, it pushes liquid brake fluid through a long straw-like tube. It goes from your brake pedal all the way to the calipers of the braking mechanism on your wheels. And because liquids do not change volume, when you push on one side, it has to push on the other side. So instead of a cable snapping or something like that, which can happen, and cables have to go in straight lines, you can route brake tubes around corners, curves, and when you push on one end, the liquid will transmit the force without losing volume, without changing volume. It will transmit the force through the curved brake line to the brake pads. Okay, that's because liquids can change shape, hence the curved brake lines, but not volume. We call that hydraulics, by the way. If you've ever heard the word hydraulics, it's the property of liquids to be able to transmit force because they do not change volume. Now, if we continue to add energy to that collection of particles that we refer to as a liquid phase being where the particles are close enough together and slow enough that they feel each other's attractive forces and it affects their behavior, it affects their flight path, it curves it. If you continue to add energy to a liquid and you increase the speed of the liquids, they begin bouncing off each other fast enough that they can break free of each other's attractive forces, they can push against any atmospheric pressure, and they will vaporize. They will boil. They will turn to vapor to the gas phase. In a gas phase, the particles are completely separate, and they're moving so fast, that they do not feel each other's attractive forces. And when they collide so violently and so elastically that they don't hang around. They hit and bounce. They're gone. Now, what kind of speeds am I talking about? Well, at room temperature, 25 Celsius, the average air molecule is moving 500 meters per second. So right now, our face, our eyes, our fingers, our head, every part of us is exposed to the air in our room. We're being struck by little tiny bullets going 500 meters per second. That's 500 football fields. No, excuse me, that's 5 football fields per second. 500 meters per second. So in a gas phase, the particles are moving so fast, again, primarily translationally, from point A to point B. They're moving so fast that they collide elastically. They bounce off each other. They don't stick to each other. They collide and bounce so fast that there's no stickiness. So when you have a gas, it's because you've added energy to a liquid. And the liquid particles begin moving faster and faster. And they begin, even though they're still sticking to each other, as you increase their speed, they begin colliding so much, so violently, that they bounce off without attracting. They hit and bounce. Okay? Imagine you're at a skating rink. You go to a skating rink, and you're having a nice skate with your friend. The lights are down. They say couple skate. You're holding hands. You're skating together. You look at each other. You smile. Everybody else is enjoying their little couple skate. You might bump into somebody. Oh, I'm sorry. Excuse me. You know, it's okay. It's crowded. You know, and you know, it's just mellow. Nobody gets hurt. It's couple skate. The lights are down. It's romantic. People are moving. It's fluid. But nobody gets hurt when they actually bump shoulders. Then all of a sudden the lights come up. They blow a whistle, and there's this guy in a referee uniform skating around with orange cones, dropping them on the skating floor, and they say, all right, speed skate. And all the like hot dog skaters get out on the skate floor, and they're like zipping around. They're going so fast. You've never seen people go so fast. You would never, ever imagine skating out in between those people and trying to hold their hand, because you would get crushed. They would collide with you. Helmets would fly, skates would fly, wallets would fly, glasses would fly. That collision would be violent. There would be no stickiness. There would be no romance there. It would be pain and hurt. That's a gas. Okay? What else do I? Oh, in gases, you can change their shape and their volume. You can change their shape and their volume. That's why we have scuba tanks. You can compress the air. Bicycle pumps compress the air and squeeze it into tubes, which make the tubes swell up because they have more particles in there than outside of there. You've changed their volume and their shape. Now, it is possible to achieve another phase of matter that most people don't think about. If you continue to add energy to this system of particles, where they're closely packed, then they're spread out, then they're really spread out and really fast as a gas, you could still add more energy, and you can cause the collisions between the particles to become so violent that the actual particle falls apart in pieces. In other words, you can make gases strike each other so fast that for a brief moment, the electrons, the negative particles on the outside, fly off, and they form 2 charged particles, positive, negative, and that's called plasma. So there are 2 types of properties in general. That we talk about physical properties, and we talk about chemical properties. Physical properties are the properties of matter that are produced by how the particles are organized, how they're moving. Physical properties can be observed without changing the material. You can look at a color of something without changing the color. You can You can determine the texture of something without changing the texture. On the other hand, and it might help to understand what I mean by physical properties are properties that you can observe without changing the material. Physical properties are properties due to how the particles in it are arranged or how they're moving. It might help to contrast that with the other property, type of property, chemical property. Chemical properties, listen carefully, this is very important. Chemical properties are the result of the electronic structure of the material. Chemical properties are any characteristics of a material that are determined by the organization of the charges. Chemical properties are any characteristics of a material that are determined by the organization of the charges in the material. Now, those charges are electrons, but we're not there yet. So I'm happy if you just understand that chemical properties are characteristics of a material that are determined by the organization of the charges in that material. Remember, physical properties are determined by simply the organization of the particles as a whole. Are they stacked? Are they rolling around? Are they zipping around? In other words, are they solid, liquid, or gas? How fast are they zipping around? That would be their temperature. How many of the particles are there? That would be mass. How much space do those particles take up? That would be volume. Those are all physical properties, and they're determined by the number of particles, the organization of the particles, how they're moving around. Chemical properties are determined by the electronic structure, the charge distribution, the charge organization of the material. And chemical properties can only be determined by changing that structure. Chemical properties can only be determined by changing the charge. All right, so some time ago we talked about where the universe came from. We talked about the explosion of the Big Bang. We talked about particles being blasted out into the universe out of nothing, probably balanced out by a negative version of the universe somewhere. And we talked about how the sun turns individual protons into helium by squeezing them together in a process called nuclear fusion. By squeezing a proton and a proton together, you get two protons, and two protons is called helium when they're stuck together. 3 is called lithium. In other words, the number of protons stuck together determines the element. Write that down. So I'm going to give you a definition of an element. It's probably going to be a Beethovenism. It's going to be kind of a unique definition based on a bunch of different sources. An element is a particular number of protons stuck together. Through nuclear fusion, so, for example, or as we like to say in mi país, por ejemplo, one proton equals hydrogen. Two protons would just be like this, and that equals helium. You see, these are all the elements that make up our periodic table. Well, there's the periodic table up on the wall. Every one of those symbols, every one of those squares is a different kind of atom known as an element. And what distinguishes one element from another is how many protons are in the nucleus. So 3 protons, when 3 protons get squeezed together, it makes something called lithium. The amazing thing about this, Sam, is we absolutely know every single kind of element that exists. There's no missing elements. There's no mystery elements on planet X. We're not going to fly a spaceship to some mysterious planet and find some mysterious element that's going to cure every problem we ever had or weaken Superman or anything like that. We already know what all the elements are. In fact, we have names for every element, even the elements that haven't been discovered yet, based on the number of protons in the nucleus, using Latin and Greek prefixes. For example, hydrogen with 1 proton is called unium in a certain naming system. Helium with 2 protons is called bium because bi means 2. Lithium with 3 protons is trium. So if you look up there at the periodic table again, you'll notice elements 113, 114, 115, 116, 117, 118. I've pretty much handwritten the symbols. If you can see from there, I don't know if it's focused or not. But those handwritten names down at the bottom of the periodic table, UUT, UUQ is actually machine printed, UUP, UUH, UUS, UUO. Those elements have not been discovered yet. Now, there's some debate over it. People are racing like crazy to get their name on an element. So they have been, some people have claimed to have made them, but they've not been verified yet. Because they've not been verified, we don't consider them to have been discovered officially yet, and so they don't have official names. But notice, let's look at 114. 114 has been confirmed. That's why it's machine printed. One in Latin is uno, in Spanish, right? Uno, dos, okay. Uno, that's what the U stands for. That's from the Latin uno. And so 114, un, quad. Quad is the Latin word for four. Un quadium. Like you may have heard of a quadrangle, or maybe you've heard of a quad ATV. A quad ATV has four wheels instead of a tricycle ATV with three wheels, the old Kawasaki's. So un quad is 114, and then they just tack on ion. So those numbers on the periodic table that I'm calling out, 114, that's actually the number of protons that are stuck together in the nucleus. So you can see that we have every element. The only ones we don't really have are the ones that are UUQ, UUP. Those have not been confirmed yet. Furthermore, the ones that are white with a black outline, those don't occur in nature generally. We have to make those in super colliders. We have to crash the protons together. We have to squeeze them together artificially, and then they generally fall apart in billionths of a second, which is why they don't last in nature to be found naturally. But that's what an element is. An element is a particular number of protons stuck together in a nucleus. Now, if you look up the definition of an element, you'll find more information. They have unique chemical properties. Each element has unique chemical properties and physical properties. And that's because adding more protons in the nucleus does a couple things. Physically, it changes things like the shape of the nucleus. It changes the mass and the density of the atom. By adding more protons to the nucleus, you're going to affect the physical properties of that atom and that group of those atoms because you're adding physically to the nucleus. You're changing its shape, you're changing its mass, you're changing its density. So each element is going to have unique physical characteristics such as density. Okay, we'll leave it at that for now. But in addition to having unique physical properties, each element also has something called unique chemical properties. And that's because every single proton will attract one electron. Protons are positive, electrons are negative. You guys should be learning about that as you're studying your epic rap battle, the structure of the atom, how you got conceived of the atom. Protons are positive parts. That's why there's a plus sign on my drawings. Each positive proton will attract one negative electron. And listen carefully, this is super important. This is the basis of chemistry. It is the electron structure around the protons. It is the electrons around the protons. It is the way that they're organized that determines chemical properties, chemical behavior. What are chemical properties? Chemical properties are the properties of a substance that are a result of how those electrons are organized. Chemical properties are the characteristics of a substance that are determined by how the electrons or how the charges, the negative charges, are organized. So physical properties are simply the result of physical things like mass, the number of particles in the nucleus, the shape. Okay? Physical properties can be observed without changing the substance. You can weigh it, you can see it, you can feel it without changing it. For example, physical properties of this paper. Well, it's about that tall. Yeah, it is. What is that, about 4 or 5 inches, right? That's a physical property. It's about 8.5 inches that way. It's flat, it's white. By describing this piece of paper, I have not had to change this paper at all. Those are physical properties. Physical properties are the characteristics of material that can be observed without changing it. Chemical properties, go back now, chemical properties are the result of how the electrons are organized around the nucleus. We cannot determine that. We cannot determine how those electrons are organized without tearing it, without burning it. Now, tearing it's not actually chemical. It's still paper, right? Let's say without burning it, without electrifying it, without soaking it in acid or something. The way we determine how the electrons are organized in a material are by chemically changing it, by altering the composition of it. When that happens, we can then deduce how the electrons work. Okay, so physical properties are characteristics that can be observed without changing the substance. Chemical properties are the characteristics that are dependent on the way the electrons are organized and can only be observed by changing those. When you change the way the electrons are organized, you change the material, you change the substance. Does anybody need me to repeat anything there? I am going to be asking a quicker question or two today. Make sure you're paying attention, because some of you noticed that's a pretty serious grade. It carries a quiz level grade, so please pay attention. Don't get distracted. All right, so elements are different numbers of protons stuck together in a nucleus. They are, an element is a specific type of an atom, where an atom is a number of protons surrounded by a number of electrons in general, without being specific. It's just, an atom is a particle made up of protons in the center, surrounded by electrons. An element is a specific flavor of atom, based on the number of protons, specifying the number of protons in the nucleus. So an element is a specific number of protons joined together. Any collection of single protons would be hydrogen. If you got double, did I say electrons? I meant protons. Any single proton, any collection of single protons is hydrogen. Any collection of pairs of protons would be helium. The element is a specific number of protons stuck together in a nucleus surrounded by an equal number of electrons. What else? Number 3. I'm looking. Elements. Okay, you cannot break an element down. Elements are already elemental. That's what that means. They're fundamental, elemental. Like elementary school is the basis of education. Elementary elements are the basis of matter. You can't break them down any further and still have elements. Like you can't take a silver atom and break it down anymore. It won't be silver anymore. Obviously, if elements are determined by the number of protons, if you change the number of protons, you've changed the element. You can't break an element down, because then you would be breaking its nucleus and you would be changing the element then. Anybody have a question about that? Okay, the next point there is that elements are organized in the periodic table. Well, let's see. If you look at it once, does anybody know how the elements are organized on the periodic table? That's right, by atomic number. Don't say mass. If you think it's mass, there's at least 2 or 3 instances on the periodic table where they're not in order by mass. Now, it looks like they're organized by mass, which is the number with the decimal places on it. But if you look at every single element where it is and look at their mass number, there are a couple instances where the mass gets lighter, because they're not organized by mass. They're organized by the number of protons in the nucleus. So that's the whole number up in the top right corner. So you got 1, 2, 3, 4, 5, 6, 7, 8, all the way to 118. And that's it for now. I think whoever invents element 121 protons, is going to win the next Nobel Prize, because that's going to form a new periodic table. It's going to have a new set of rows. But that's a whole other topic, another chapter. So elements are organized on the periodic table by the number of protons. A compound. Well, the word compound tells you what it is. Compound means multiple. Like if you have a compound fracture, you have a serious break in your arm or leg that has multiple breaks. A compound in chemistry is made up of 2 or more elements joined together electrically. A compound is 2 or more elements joined together electrically by electrons. That means it's a chemical thing. But remember, physical property is size, shape. It's just determined by some physical things like mass and amount. Chemical properties are the properties or characteristics that are a result of the organization of the electrical charges. So if you put together 2 elements with each one has some unique electronic structure, if you put them together, you've now changed that electronic structure. You use the electronic structure of each to make something new. That's called a compound. Now, compounds, even though they're made of more than one element, they're not the same as mixtures. Mixtures are like Kool-Aid or Gatorade. If you play sports and you mix up your own Gatorade, like you get the big orange igloo cooler and you dump a can of Gatorade in there and then you add water. Well, hell, if you run out of Gatorade, if you run out of the powder, your Gatorade is going to be dilute, but it's still going to taste a little bit like Gatorade. In other words, the recipe for Gatorade is variable. It's not written in stone. I mean, it's suggested, but you can make it stronger if you like your Gatorade stronger. You can put an extra teaspoon or two in there. That's a mixture. When you can change the recipe of something, that's a mixture. When there's a fixed recipe, it cannot be altered. When there's more than one ingredient, but it is written in stone by the universe, like water is H2O. Water is never H3O. Water is never H2O2. In fact, if you drink H2O2, you'll get really white teeth and die. H2O2 is called peroxide, hydrogen peroxide. So if you change the ingredient in a compound, you no longer have that compound. A compound is two or more elements in a fixed ratio, in a fixed recipe. Okay, two or more elements that are combined together in like a permanent, never-changing recipe. Water is always going to be H2O. 2 parts hydrogen, 1 part oxygen. It will never be different from that. If you make it different from that, you no longer have water. You got, like I said, if you add an extra oxygen to water, you now have a poison. Now, we put it in our mouth, but it's dilute. When we brush our teeth or you put it in your hair, it whitens things. It lightens the color of things, like your teeth. If you gargle, there's certain mouthwashes that have a little bit of peroxide in it. Sometimes you brush your teeth with a peroxide that's in that brown, container, but that's only 3% peroxide, 97% water. If you drank 100% peroxide, your mouth would burst into flames. Those bubbles that come up on your sores when you put peroxide, that's hydrogen gas and oxygen gas. If you put 100% on a cut, you would burst into flames because it would combust. That would be spontaneous combustion. All right, maybe that's what's behind spontaneous combustion. Maybe people are messing around with pure hydrogen peroxide. There's no evidence of it when they don't. Anyway, so again, a mixture has a variable, changeable recipe. A compound does not. A compound is made up of 2 or more elements joined together chemically, electronically, in a fixed ratio. Cannot be changed. Any questions? I'm looking at compounds are chemical combinations of 2 or more elements. I already said that. Forget about the law of definite proportions. Forget about the law of multiple proportions. We're moving on. Anybody have a question? Oh. If you don't have questions, I might have a question for you called a bell ring. Called a clicker question. Mixtures of matter. We're breathing a mixture right now. It's called air. Air is a mixture of primarily nitrogen. It's like 80% nitrogen. Call it 79% nitrogen. Like 19 or 20% oxygen, and the rest is a little bit like 1% carbon dioxide and water vapor. A little bit of argon in there too. So what's a mixture? Remember, I said a mixture is 2 or more materials, 2 or more substances that are combined not chemically, they're combined physically. That means they can be separated. That means without changing the electronic structure, you should be able to separate things. There's a company in Doral called Airgas, and they have a big refrigeration system that has multiple refrigerators, and they just take a big volume of air like this room, and they chill it. And then it gets moved to another container that chills it even more. And then it gets moved to another container, and after about 3 or 4 refrigeration cycles, they make it into a liquid. You have liquid air. And then just like oil and vinegar, it separates out into layers. And you get a layer of carbon dioxide, you get a layer of nitrogen, you get a layer of oxygen, and they separate that and they put it in bottles and sell it to hospitals and research facilities. You get a tank of carbon dioxide at Burger King, you make your fizzy soda. You get a tank of helium at the doctor's office so that your MRI machine works. You get a tank of oxygen at the hospital so that you can keep people alive. You get a tank of oxygen at the welding place so they can have really hot torches. They can separate this mixture of air simply by refrigerating it down until it turns to a liquid. Now, air is a certain kind of mixture. There's two kinds of mixtures. There's a kind of mixture where you can't see the difference between any part of it. Like in this space between my hands is air, but the air that's here looks the same as the air that's here. It's clear, colorless. Now, that's a special kind of a mixture. When you have a glass of Kool-Aid or a glass of Gatorade where there's no ice, it's just a drink. When you have a mixture where you cannot see the difference between one part and the other, air, tea, a glass of tea, a glass of Kool-Aid, when you can't see the top looks different from the bottom, the left looks different from the right, if it doesn't look different in any part, I think it's Greek for same. It looks the same on the left and the right, top and the bottom. The Greek word for that is homo. And so we call it a homogeneous mixture. Not genius like intelligent. It means the root genus in homogeneous, it comes from the same root that we get gene, as in like your DNA, or generate, which means to make. So you can see the connection between gene and generate, because it takes genes to make a living being, right? So gen, G-E-N, is a root. It means to make. So a homogeneous mixture means to make it the same throughout. So it's actually kind of an active word if you think about it. So when you put sugar into your tea or your coffee and you stir it so that there's no lumps and you can no longer see the sugar, you're making it the same throughout. You're producing a homogeneous substance. When you put your sugar in your coffee and you stir it up so you can't see any particles, it's going to be sweet at the top, it's going to be sweet in the middle, it's going to be sweet at the bottom. If you don't stir it up and put the sugar in there, you take the drink at the top, it's going to be bitter. In the middle, you're going to start tasting a little bit of the sweetness, and then when you get to the bottom, you're going to have like syrup. That's not homogeneous. You did not make it the same top and bottom. So we call that hetero, because the Greek word for different is hetero. And it's different at the top than it is in the middle and from the bottom. So if you can see or detect a difference in the mixture from top to bottom or left to right, it's no longer considered homogeneous. If you can see differences or detect differences, then it's heterogeneous. So what do you think about the air we're breathing? Is it homogeneous or heterogeneous?
Isn't it homogeneous?
It is, because we can't see a difference in it. Now, can anyone think of an example where the air is heterogeneous?
Maybe when it's foggy.
When it's foggy, you'll see a layer of a vapor, and that's different from above it or below it. Yes, sir.
Steam.
Steam. When you're cooking and you see the vapor coming out of the pot, because you can see a difference in the air over the pot versus next to the pot, then that's heterogeneous. If you see somebody smoking a vapor or vaping in their car and they fill the car up and then the window rolls down and a cloud of vape comes out, that's heterogeneous. That's not homogeneous anymore. Same thing with smoke or clouds. Okay, so whenever you can see differences in the mixture, then we say that's heterogeneous as a mixture. Okay, if you look at the floor, the tiles on the floor are heterogeneous in our classroom because they have different colors. The tabletops are mostly heterogeneous. They have different colors, Now, my desktop, the black desktop there, that's primarily homogeneous. It's a homogeneous mixture because the composition of it is consistent. It's uniform. It's the same throughout. Anybody have a question about homogeneous or heterogeneous?